Hey guys, I know that there were a lot of the juniors that were gone from 6.2 for the 6.2 lesson that was on Wednesday, so I figured that I would post a video on this, especially because it can be kind of tough, so I'll go through this video explaining 6.2. So 6.2 is about graphing rational functions. Um, and rational functions is a rational function is a function that has a polynomial in both the numerator and the denominator of a fraction. Um, so the parent function is for the rational function is 1 divided by x. Ignore that little mark right there. But 1 divided by x is the parent function. And it consists of two symmetrical parts called branches. So you can see the parent function right here. And so the two branches that it's talking about is this one right here and this one right here. And so I kind of want to spend a little bit talking about the behavior and why does it behave this way. So first thing to consider is the expression 1 divided by x. You guys have to know that because x is a variable means that it could be any number. You could substitute x with any number that is in the domain of x, that is a value of x. So we could plug in 2, we can plug in 4, we could plug in -1, so on and so forth, but we cannot plug in 0. So you can see that this function never crosses the y-axis, and that's when x is equal to 0. And we learned in chapter 5 that these lines are called asymptotes. So the vertical asymptote right here is x equals 0. So you cannot divide by 0. It's an undefined expression. You can't assign a value to it, a number value to anything divided by 0. So anything divided by 0 is undefined. You just can't associate it with any sort of definition or value. So it's undefined. And with that being said, so because this expression, because x cannot be 0, well, let's look at the y value. So why is there a horizontal asymptote? The horizontal asymptote at y equals 0. So it's kind of a result of the fact that you can't plug in any values that are less than, or you can't plug in any, well, let's say this. If y is equal to 1 over x, if I experiment with what I plug into x, so let's say I plug in a very large number for x, very, very large number, well, even a small value, so let's say we plug in 4. So if we plug in 4, we get 1 over 4, and that's equal to 0.25, and that is close. That number itself, 0.25, is already pretty close to 0 itself. So so if x is going to be equal to 4, y is going to be 0.25, which is close to 0. And so imagine what happens if we let x get larger. So even if we plug in x equals 10, so y will be equal to 1/10. Let's say x is equal to 100, so y is equal to 1/100th. Y is equal to a million. That's 1 over 1 million, which is a very small number that is close to 0. So y will infinitely get close to the value of 0, but never actually be 0. So it makes that behavior in both directions. And so that is why there is a horizontal asymptote as well, because this expression y equals 1 over x, just no matter what the size of x is, it will get close to 0, not equal to 0, and it makes that behavior as you go to those ends. So that's why there's a horizontal and a vertical asymptote for the rational functions. Okay, so yeah, so there's the vertical asymptote, that's x equals 0. There's the horizontal asymptote, that is y equals 0. So there they are. Okay. All right. So really, we're just going to plot some points. I'll give you guys some tips and pointers on how to graph some rational functions. Okay. So starting with these ones right here. So -5 divided by x. Okay. First of all, let's graph 1 divided by x. So f of x is equal to 1 divided by x. This is the parent function. So what I'm thinking about numbers that I can plug into this function right here. So if I make a table of x and y, and I know y is equal to 1 over x, so really the only good number that I could plug into this function is 1, I guess you can kind of say. So x equals 1, well that means y is going to be equal to 1 over 1, which is equal to 1. So 1, 1, I get a point right here. Let's say I plug in 2. Well, if I plug in 2, I get 1 over 2, which is 1/2. So if I plug in 2, I get 1/2. And if I plug in 3, I get 1/3. If I plug in 4, I get 1/4. And again, you can kind of see that pattern that it's just going to approach the asymptote. So what I like to do first, honestly, is to draw in my asymptotes, because that will help me with my lines of the graph. Okay, and then let's say I plug in 1/2, for example. 1/2 would be right here on the x. Well, then that means y would be equal to 1 divided by 0.5, which would be equal to 2, because 0.5 can go into 1 twice. So right there, and it's going to make a similar pattern in this direction, just like that. Okay, but remember that there's a second branch as well. So the second branch comes from plugging in the negative numbers. So let's say x is equal to -1. Well, we'd get 1 over -1, which would be -1. So I get a point here. Okay, now I usually don't typically graph the other branch because these functions are actually symmetrical about the diagonal line that's right here that runs through the intersection of the asymptotes. So this point, which came from going right 1, up 1, there's actually going to be point left 1, down 1. And then this point right here, which was right 2, up 1/2, well, there's going to be a point over here, left 2, down 1/2. So I usually just use symmetry to graph the rest of my function. So, and my asymptotes, I just make these lines go close to my asymptote. Okay, so this is the graph of 1 over x. It's the parent function. Now let's graph the function g of x right here. So let's make this equal to -5 over x for equal to y. Now, because of the fraction, again, we want to be careful with what we plug in so that we don't get, like, I don't want to plug in 7, for example, into this function, because -5 over 7, that doesn't give me a very nice number to graph, right? So I like to plug in numbers. So if 5 is my numerator, I want my denominator to be factors of 5, so that way I get nice whole numbers. So I want to plug in, say, -5, -1, or 1 and 5. Those are the numbers that I want to plug in. So if I plug in -5, well, I get -5 over -5, and that's going to be +1. So 1, 2, 3, 4, 5, and 1, I get a point there. If I plug in -1, I get -5 over -1. That's going to be equal to +5. So -5 and 5, so that's going to put a point right here. Okay. I'm not going to plug in these positive numbers because, again, I'm just going to use symmetry. Excuse me. I'm going to use symmetry. But also notice that my points are in this quadrant over here rather than over in this quadrant, these two quadrants. That's because my coefficient in the numerator is -5. And so that negative Well, we know if we multiply something on the outside by a negative, that's a reflection in the x-axis. So had this been 5 over x, my branches would have remained in these two quadrants, but now that's negative 5 over x, they're going to be in these two quadrants because of a reflection that's happening in the x. Okay, so since this point was over 1 up 5, there's going to be, I'm going to reflect that over this line that's happening right there. So there's going to be a point right 1 and down 5, right 5 and down 1. 1, 2, 3, 4, 5 and down 1. Now the only other point I would care to really graph would probably be negative 2. So I'd get negative 5 over negative 2, which would be equal to 2.5. So negative 2 and 2.5, which would put the point right here. And there you go. That might be an okay one. That means if I plug in 2, I'd get negative 2.5. Okay, so then I should have the points. And again, I use my asymptotes to help me guide the lines to where they're going to go on the end, at the ends. So I'll just draw a line through my points and then draw them going towards my asymptotes. And there you go. So that's a easy way to graph those, I think. Now you can also use the fact that this is a stretch, and so say that I had hypothetically, let's cross this out, and instead of that, let's say I have 4 over x as a hypothetical. Well, the parent function has points here and here, right? But because of this stretch, instead of being there, then I'm going to have this up stretched by 4. So instead, I would draw a point right here up 4 units and this one down 4 units. Okay. So yeah, that's what I would do as a method if you want to if you're looking to find quicker ways to graph points rather than just plotting points. Okay. Also notice that because of the fact that you can plug in 5 and negative 1, so remember how we plugged in 5 and we got 1, or negative 5 we got 1, and we plugged in negative 1 and we got 5. Well, this is also going to behave similarly, where I'll have a point over 4 and up 1 as well. Okay, so then left 4, 1, 2, 3, 4, and down 1 as well. Okay, now there is also a third number that would be nice to plug in, because 4 is also divisible by not just 4 and 1, but also 4 and 2. So 4 over 2, which would give me 2. So if I plugged in 2, I would get 2. If I plugged in negative 2, I'd get negative 2. So these are my points. My asymptotes are here and here. Okay, and then I get my graph, just like that. Okay, and there you go. That's how you'd graph 4 divided by x. I'm going to come down here, I'm going to cross that out, and I'm going to do y is equal to negative 2 over x to just give one last example. So because it's negative, again, I'm going to have branches that are in these quadrants right here, rather than here in these quadrants. And because my factor is 2 on the top, instead of being here and here, I'm going to stretch the distance by 2. And I also know that I'm going to have the ones over here, so not just over 1 and up 2. Oh, whoops, I put that in the wrong spot. Right here, here, and I put that one in the wrong spot too, here and here. So not just over 1 and up 2, but up 1 and over 2, and in the other quadrant in the same manner. And then I have my asymptotes like this, and there we go. So again, try and find the patterns. I hope that these patterns and these behaviors will help you, so that it makes the graphing these a little bit easier. Okay, I'm going to move on. So just to be as a reminder, so this is for any rational function that is of the form of a divided by x. A could be any number, any real number, so keep that in mind, because we're going to cover different forms. Okay, so the next form of a rational function looks like this right here. So these are going to look very similar, but these types of rational functions are going to be translated, meaning that there's going to be horizontal and vertical shifts. Okay, so you can see that we have x minus h and plus k. So this should look familiar to just about every other transformation of graphs that we've ever covered. So if you guys remember quadratics, we had x minus h squared plus k. So if I had a quadratic that was x minus 2 squared plus 5, well, this was a shift to the right 2 and shift up 1. And so that's it's the same idea. So let's go ahead and talk about this right here. So for this function right here, remember that the typical parent function has asymptotes that run on the x-axis, but because asymptotes can be affected by shifts, you have to move them as well. So x plus 2 is a shift in the left direction, left 2. Now, that won't affect this horizontal asymptote. I can't move this to the left because it's just going to remain horizontal, but I can move this to the left, and that will change. So 1, 2. So my asymptote is going to be moved over in that direction 2 units. Okay. All right. Whoops. Okay. And with that being said, there are different ways you can think about this. You can plug in numbers. Since the numerator is 3, you want the denominator to be either 3 or 1. So you have to think about numbers of x that would give you 3 and 1. So, for example, let's say I make a table of x, and then I have negative 3 over x plus 2. I'm actually going to give myself more room. Move this over here. So 1 would be a good number to plug in. The reason why I say that is because I'd get negative 3 over 1 plus 2, and I'd get negative 3 over 3, which would be equal to negative 1. Okay, now I just want to caution that x equals 1, y equals negative 1. What even I tend to do, and what other students will do, is they'll count from this as if it were the origin. So they'll go right 1, down 1. Now, the problem with that is that this is not the origin. So this 1, negative 1 should be counted from the actual origin of the x and the y axes. So x is 1, y is negative 1. So that's where you would want to plug in the point right there. Okay? So there you go. Now, another number that you might want to plug in could be negative 1. So if I plug in negative 1, I'd get negative 3 over negative 1 plus 2. That would be negative 3 over, that would be positive 1, so that's going to be negative 3. So again, I'm not going to count negative 1, negative 3 from here. Negative 1, negative 3 would put me right here. That's not correct. I'm going to count negative 1, negative 3 from here. So negative 1, 1, 2, 3, right there. So negative 1, 1, 2, 3. That's where I'd plot my points, like that. And I'd go just like this. Okay? Now, this is what I can use this intersection for. I know that from this intersection, not the origin, this is down 1, right 3, right 1, and down 3. I can use that same behavior reflected about the origin, or mirrored about this line right here. So right, left 1, and up 3, up 1, and left 3. So that's how I would finish it, like that. Okay? Okay. Now, I'm going to backtrack a little bit and show you another way that you could go about this if you don't want to plug in points and potentially make any errors. So after making this shift left 2, you could use the 3 negative 3 over x function to help you. So say that I didn't have a shift. If we think about this function right here, it's negative, so the branches are going to be top left and bottom right, top left and bottom right, and 3 over x would be left 1 and up 3. So again, if we were to consider the function 1 over x, if this function were shifted to the left 2, it would have points here and here. Just right 1, down 1, left 1, up 1. I guess I should say negative 1. But in any case, since it's stretched by a factor of 3, you can just take that into account. So right 1 and then down 3. 1, 2, 3, left 1 and up 3. And then 1, 2, 3 like this and that. So you could use that if you're comfortable doing something like that. You get the same thing. So let me give maybe a more clear example in 17. So in 17 we have both horizontal and vertical shifts. So I'm going to graph my asymptotes. Okay, now this is going to be a left 4 shift. So that's going to move this line right here. 1, 2, 3, 4. And this one is going to move down 1. Okay, now look at my numerator, and it's negative 3 over x. So negative 3 over x, if I were to compare it to, I guess you could say, a parent function. Well, negative means it's going to be in these quadrants right here. Okay, and because it's 3, I take the point that's right there, that would have been from 1 over x, and I'm going to shift it or stretch it by a factor of 3. So that would be here, and that would be here. Okay, well, because it's stretching that by 3, then it's also going to go this way by 3. So 1, 2, 3, right there, and then 1, 2, 3 over here, just using symmetry to graph the rest of it. Okay, and so that's how you can think about it. I think that's a much easier way to go about it. I don't really like plugging in numbers, especially because I fall victim so like 1, negative 1, I often fall victim to counting it from here rather than here, and that messes me up all the time, which I do not like. So that's something you could try. Let's try one more, or maybe even 2 more. But instead of this, we're going to say, let's try negative 4 over x plus 2. So first start by drawing my asymptotes. Okay, and I have a shift that's going to be to the left 2. So I'm going to take this and move it left 2 like that. Okay, and then I'm going to just think about, well, negative 4 over x. What's that going to be? Well, I know that it's going to be in the top left and bottom right quadrant because it's negative. Okay, and then it's stretched by 4. So 1, 2, 3, 4, and then 1, 2, 3, 4, and then 1, 2, 3, 4, 1, 2, 3, 4. And I can also, again, 4 divided by 2 is 2. So I know that this is going to be left 2, down 2 from here. Left 2, down 2 from there. And there you go. So again, just trying to think about quicker ways to graph these, because that's always better. Let's try one more. Let's try, instead of graphing this, let's do 1 over x minus 3 plus 2. Okay, so I'm going to graph my asymptotes right here and right here. Okay, this is a shift to the right 3, so that's going to move this axis, 1, 2, 3, and then I'm going to move this one up 2, that's going to be this asymptote up 2, like that right there. Okay, and then if I just think about 1 over x, well, since it's positive, then I'm going to be in the top left and bottom right quadrants, and from this spot right here, since it's only 1 over x, there's no stretch happening, so there you go. That's the only point I would plug in. So going down like this and going out to the right like that. Okay. Now that's how I would do those ones right there. Alright. Now one other thing to go over, we didn't talk about domain and range. So it does say to state the domain and range for these. Okay. Now the domain and range depend on your really depends mainly on your asymptotes, where they are at. So you can see that for the domain of this function right here, that it goes forever to the left over here. It's going to come along, and you can see that it comes up, and then it's going to jump straight up. And it's never actually going to be, so this is the line x equals -2, so it's never going to touch that line because it's an asymptote. Okay, well this function over here never touches -2 either, but it gets really close to it, but it also goes over this way for infinity. So the domain actually covers all real numbers except for wherever the asymptote is. So if this is the asymptote at x equals -2, then the domain can be everything, so all real numbers except -2. The domain cannot be the asymptote because it can't cross the asymptote. So all real numbers except -2. The range also behaves very similarly. So the range, if we look in the y direction, well, it goes down this way forever and it comes up, and it's not going to be y equals 0. That's what this asymptote is, y equals 0. Okay, so it's never going to cross that line. And then this branch right here never crosses it either, but it also goes up forever. So the range is all real numbers, but y cannot be equal to 0. Okay, so this is the line, just kind of now realizing that I didn't shift my axis down 1 on this one, but that's whatever. So this one right here, since it was shifted down 1, the range would be y cannot be equal to -1, and the domain is that x cannot be equal to -4, because that's where the asymptotes are. For this one over here, again, I look at my asymptote. So this is y equals 0, so my range is that y cannot be equal to 0. And then this is the asymptote x is equal to -2, so my domain is all real numbers, but x cannot be equal to -2. Okay, so that's how I do it. So this the domain here is that x cannot be equal to 3, and the range is that y cannot be equal to +2. Okay, so hopefully that's a good enough explanation for that. Okay, coming down here for the last part. So there are 3 types of rational functions: a over x, and then we talked about a divided by x minus h plus k. These are functions that behave very similar to the parent function, just maybe with a stretch. These are also with a stretch, but also with translations. And then there's these ones right here, which is ax plus b divided by cx plus d. Okay, so for this one right here, these ones are not as friendly to graph, but I'll show you how you can make them friendly. These are often more friendly to graph, but we'll talk about how we can make these ones better. Okay, so there's 2 different ways. So first thing is to talk about the asymptotes, okay? So when it's in this form, you need to find the vertical asymptote. Okay, so vertical asymptote. So you can find the vertical asymptote always for any type of rational function by, well, vertical asymptotes are always x equals 0 or x equals some number, so keep that in mind. But you should set the denominator equal to 0 and solve for x. Okay, so for this example here, if I want to find the vertical asymptote, I'm going to take the denominator, so x minus 3, set it equal to 0, and solve for x. So in this case, x will be equal to 3, and that's going to be the vertical asymptote. So 1, 2, 3, right here. Now, you might be thinking, well, that's not different from, over like what we'd experienced in the previous examples. Yeah, that's true, but let's say that down here for these examples, notice that it's not going to be quite the same. I can't identify the shift just from looking at that right there. You can, but it's not as obvious. So again, if I want to find the asymptote, so the vertical asymptote for this, I'll take 4x minus 8, I'll set it equal to 0, so I get 4x is equal to positive 8, and x is equal to 2, so that's where the asymptote is going to be, right there. Okay, for this one right here, so I take the denominator, negative 2x minus 3, set it equal to 0, solve for x, so I get negative 2x is equal to 3, divide by negative 2, and x is equal to 3 over negative 2, so that's negative 1/2. Okay, so that would be probably like right here. Okay, so that's how you could find your vertical asymptote. And again, this means that the domain is that x cannot be equal to 2, and the domain here is x cannot be equal to negative 3/2. Okay, all right, well, now let's talk about the horizontal asymptotes. So the horizontal asymptotes will always be y equals, okay? And it's pretty simple, but no real, I don't have a great explanation as to why, but it's the leading coefficient of the numerator divided by the leading coefficient of the denominator. Or you can say A divided by C. Okay, pause if you need to write that down because I'm going to keep going. So this is the form that it's in. So A is the leading coefficient in the numerator, C is the leading coefficient in the denominator. So it will have a horizontal asymptote at the leading coefficient here is 2, and the leading coefficient in the denominator is 1. So 2 over 1, which is equal to 2. So we'd have a horizontal asymptote like right there. So those are where the two asymptotes would be. Okay, coming down here to these examples, the leading coefficient here is 1, so you'd have a horizontal asymptote at y is equal to 1 over 4. So that would be probably somewhere, maybe a little bit lower than that, but about around that area. The horizontal asymptote here would be at y is equal to negative 5 divided by negative 2, which is equal to 5/2 or 2.5. So that should be about right there. Okay, so that's how you can find horizontal asymptotes. Okay, now, as for the actual graphing, okay, so the actual graphing is where it gets a little bit more tricky because trying to find numbers to plug in doesn't really work. Also, this right here doesn't indicate where your branches are. Your branches could be on left or right, up and down, So say if that was negative, it doesn't necessarily mean that your branches are going to be here and here. Okay, so this isn't the easiest form to graph points. So you would just have to plug in random points. So in this case right here, I would plug in numbers that are around here. So this is x equals 1, 2. So you could plug in, you can make a table, and x and y, you can plug in 2. Okay, if you plug in 2, you get 2 times 2 plus 1 over 2 minus 3. So that's going to be 5 over negative 1, which is negative 5. So when x is equal to 2, you go down 5. 1, 2, 3, 4, 5. Okay? I was actually quite lucky that we got those. Okay? But that also means, so this point is over 1 and down 7. So there'd be a point over here that's right 1 and up 7. And then it'd be down 1 and over 7. Okay, so down 1, 1, 2, 3, 4, 5, 6, 7. And then same thing over here, over 7, and then up 7. Okay, and you could probably just do your best to draw like that. Okay, now I'm going to show you an alternative way to doing this. Okay, so let me take pretty much all of this right here. Well, we'll just take this right here. Okay, oh, I already did it right there for my other classes. Okay. Just give me a second. Okay, so here's the thing. What we kind of do, like what most students get used to, is the y equals a divided by x minus h plus k. They get used to graphing in this form because it's pretty easy to see the shifts and because it's easy to see the stretch as well. It's easy to see only the horizontal shift right here, and I guess you can kind of see where the horizontal asymptote is going to be, but it's hard to see the stretch. But I can convert this into a format like this using division. So if you guys remember, we're going to use synthetic division for this one. So synthetic division you can only use if the coefficient of the denominator there is a binomial factor and the coefficient is 1. So if you take this and you set it equal to 0 and solve for x, you get x is equal to 3, and that's your box number for synthetic division. And if you guys remember, here the coefficients on the numerator are 2 and 1, so we use those as the numbers that we put up there. We drop the 2, and we multiply this number by whatever number is in the box. So 2 times 3 is 6, we put that here, and then 1 plus 6 is equal to 7. Okay, now this is called the remainder. And this was 2x plus 1, right? That's what this was equal to. Well, because we divided, we reduced the power. This is 2 to the first power. Well, this is 2x to the 0 power, and x to the 0 power is just 1. So I would write my solution. So 2x plus 1 divided by x minus 3 is equal to 2 plus my remainder divided by my original denominator. And so this right here, I just converted into this format that's up here. Let me write it in that sort of order though. So 7 and then x minus 3 plus 2. Okay, well, that right there actually matches everything about what we said up here. Okay, so this right here is equal to each other. So again, if we were to read this like this format right here, that's a shift to the left, right 3 units. Okay, well that's where our vertical asymptote is. Up 2, that's where our horizontal asymptote is. And then we said it was stretched by 7. Well, if you go away, so go over here, 1, 2, 3, 4, 5, 6, 7. Oh, okay, and then over 7. Up 7 and over 7. So you can see that it's just another way to convert this into that right there. Okay? So very useful to be able to do something like that. Okay? Now, for something like this right here, since the denominator doesn't have a leading coefficient of 1, you'd actually have to use long division in this case. If you were going to make it work, you have to use long division, okay? Which isn't very pretty, but you can try it. But I think the only problems I gave to you guys on your homework, for the most part, are not, you don't have to use long division. I think, oh, maybe there's 2 problems, I can't remember, but in any case, just so you guys know, so that's going to do it for this lesson, but I do want to let you guys know that homework 6.2 is on paper, and it's not going to be on Big Ideas, so make sure you grab that in Canvas, or you can stop by my class and grab it in my class. Just stop by and I can give you a copy. So, okay, let me know if you have any other questions. Thanks, guys.